All right, welcome to OmegaMatters, our little show where my dad and I have casual conversations about health and nutrition, research, statistics, and omega-3 fatty acids. I'm Christina Harris-Jackson. I'm the Director of Research at Omega Quant Analytics. We specialize in fatty acid analysis, and I am also a nutritional science researcher and registered dietitian. My dad, Bill Harris, is a world-renowned scientist in the field of nutrition and omega-3 fatty acids. Recently started a nonprofit research institute called the Fatty Acid Research Institute, or FARI for short. But he did start Omega Quant over 10 years ago, so we could offer omega-3 index testing to clinicians and individuals. So today we are joined again by Dr. Nathan Tintel. And Nathan is now the executive director of FARI, I believe, but he's also a professor or expert in biostats. And so today we're going over an exciting new paper that my dad and Nathan wrote together along with the Force Consortium. So first off, do you guys want to talk about the paper?
Yeah.
Start.
Let's talk about I'll talk about the Force Consortium.
Mm-hmm.
And get right down to it. First of all, the paper was about the relationship between omega-3 levels in the blood and risk for death. Death from any cause and risk for death from heart disease, cancer, and everything else. And that was the general question. We did it within the context of a group called FORCE, which is the Fatty Acid Outcomes Research Coalition, which kind of spells force. Don't go too deeply into that. Acronyms are pretty sloppy these days. But this was started by Dr. Darius Mozaffarian, who's one of the deans at Tufts University. And Darius is a cardiologist and long-term, a very productive omega-3 researcher. But he started this group several years ago to pool together all the cohort studies around the world as much as possible that had fatty acid data at baseline and had followed different groups for different outcomes. And the idea was, let's pool all these studies together. And this is the one we published yesterday in Nature Communications was one of those studies. And again, it was on omega-3 levels as predictors of risk for total mortality. So that's the overall introduction to it.
Yes, Force is they have started to really put out a lot of interesting papers on fatty acids. So I very much appreciate the work that Force does. So with this study, you mentioned it's somewhat of a meta-analysis. Nathan, can you go ahead and talk about how this study might be a different kind of meta-analysis than what we're used to?
Yeah, so a lot of times when you see meta-analyses published out there, what people have done is they've gone to already published studies in the peer-reviewed literature, and they've tried to kind of tell an overarching story from those individual papers. So you might have lots of small papers, and some say there's an association maybe between a blood biomarker and a disease, and some say there isn't. And so meta-analysis tries to kind of pool all those results together and come up with one overarching conclusion. And that's a really laudable goal. There's a lot of strengths to meta-analyses. You get lots of different cohorts represented, lots of, usually you can represent a larger population, more diversity, things like this. But there's some serious weaknesses to meta-analyses. And one of those is that all those individual analyses that you've pulled together have been done in a different way by different people. And what that means is that there's a lot of decisions that you're making. A lot of them are statistical decisions about what covariates to adjust for. How are we going to account for this aspect of things? And so at the end of the day, sometimes the results of meta-analyses can be a little messy and hard to interpret, even though their goal is to try to tell this overarching story. So Force, and this consortium that this paper is part of, does have an advantage in the kind of meta-analysis that we do, because we all coordinate the analytic plan ahead of time. We all sit down and say, how are we going to decide what disease means in this context? And so even though in those typical meta-analyses, there might be different definitions of disease, how are we going to coordinate and harmonize that? And how are we going to do the same on the blood biomarker? And how are we going to do the same on all the covariates? How are we going to handle age? And how are we going to decide which covariates matter and all these things? And so at the end of the day, by working together and coordinating ahead of time, we have a streamlined, harmonized analysis that we all agree upon And so the story that we can tell is a much clearer one compared to a standard meta-analysis.
Yeah, that's really well said. So now that we kind of know who did it, why it's being done, do you guys want to go into some of the main findings?
Yeah, let me add one more thing to what Nathan said. Another potential weakness of traditional meta-analysis is you only deal with published papers.
Mm-hmm.
So if there's any data out there that's not published, you don't see it. And in the meta-analysis or in the paper we're talking about today, over half of there were 17 cohorts, and well over half of those had never published, never examined their own data sets for this question. So it's all brand new data. And so you get away from some of the publication bias that a standard meta-analysis could have. And it's not that we've used every cohort possible on Earth. People have, they volunteer to be part of this or not, and some can, some can't, but it's certainly a step toward more transparency and more generalizability.
Mm-hmm.
So I'll tell you what, let me share my screen if that's okay.
Yeah.
And we'll just pull up the paper and point out here that it's published here in Nature Communications, which is one of the Nature family of journals. This is a open access paper from Nature, meaning it's open to anybody. We can share it with anyone. And you can see, as you mentioned, there are a lot of different authors. Nathan and I are the first two because we kind of led the study. But all these other individuals are either PIs or the directors of a given cohort. Again, there's 17 studies here. Or they're the analysts, the biostatistical analysts who did the work. So there's a lot of folks involved with these studies. There's a lot of eyes looking at this data to make sure it makes sense. If we go to the kind of quick look, these are the cohorts. Each one, of course, has got an acronym, but you can see they're from 10 different countries without counting them here. Follow-up years, average, something like 17 or 16 years on average of follow-up from between when the blood sample was taken and when they followed up to see who had died and who hadn't, is what it amounts to. People are generally in their 60s on average, typically 50-50-ish male, female. And then over here in the far right corner is the lipid fraction in which the fatty acids were measured. And this is one of the challenges of fatty acid research, particularly epidemiology, is that different cohorts choose to measure fatty acid status in different parts of the blood. Because you can measure it in whole blood, you can measure it in red cells, you can measure it in plasma phospholipids, whole plasma, et cetera. So the way that the Force Coalition gets around this problem of mixed exposures is they say, well, we don't care what fraction of the blood you measured your omega-3 levels in. We're just going to look, everybody's just going to divide their levels into quintiles, just in 20, 20%, 20%, 20%, 20, and we're going to compare the highest and the lowest 20%, the extreme quintiles. And we know from other studies that the omega-3 fatty acids particularly and uniquely correlate very well regardless of which lipid pool you measure them in. So if it's high in red cells, it's going to be high in plasma, it's going to be high in plasma phospholipids. So our approach is to say, we're not going to worry about the exact number, the actual percent of EPA and DHA in red cells, for example. We're just going to look at the distribution within each of these cohorts of these by quintile. And then we did our whole analysis by quintile. So that's the approach we took. This, I think, is probably the most important figure in the report. And this is looking at hazard ratios, meaning risk for death between essentially the 10th percentile and the 90th percentile. So the 90th percentile, of course, is the highest omega-3 levels. 10th percentile is the lowest. So we're looking just at that spread. So asking, is there a difference in risk for death related to that difference in omega-3 levels in between 10th and 90th in each of these cohorts? And this is broken down by lipid pool. So this top half of these studies on top all measured the omega-3s in phospholipids, whether it's red cell or plasma. And as you can see over here, we're looking again at the relative risk reduction in the 90th versus the 10th. So if the dot is on the left side of this line, it means there's a reduced risk, lower risk for death in the people in the 90th percentile compared to the 10th. And interestingly, every one of these, even though they may not be statistically significant because the confidence bar confidence interval crosses 1. This is the beauty of meta-analysis. Every one of them, the point estimate is below 1, meaning there's a significant risk reduction. We then look at a couple studies that reported cholesterol esters, and the summary average here, one was right on no effect and one was a big effect. Four different cohorts used whole plasma. And again, the trend is certainly to the left. But if you average all of these together, top quintile to bottom quintile, you get to the bottom. This is the most important dot in the whole paper right there. And that is a overall hazard ratio of 0.87, meaning a 13% reduction in risk for death in people who had the 90th percent versus the 10th percent over that 16 years of follow-up. Of course, if you follow people long enough, everybody dies, and the risk for death is 100%. So we can't do that. We have to look at a window of time. And so this is roughly between age 60 and mid-70s. That's the window of time when people were looking at death. So that is the, I think, primary take-home message. Nathan, you want to add anything to that?
No, I think you made a good point. I'll clarify one thing. The beauty of this is, because you said, it's kind of an average across all those cohorts. It's a weighted average across the cohorts. So it does allow, certain cohorts that have more data to sort of add a little bit more, weight to the analysis. But part of what we also do then is look to make sure that there's no single cohort or single, for example, in this case, compartment that is driving the findings. And in this case, we were able to say that these findings were robust across those different considerations.
Great. Yeah, then the last thing I just want to show here is this table 2, which is, we not only focused on total mortality, so dead from any cause. We wanted to look at least roughly at the major bins of why people die, and typically it's cardiovascular disease, CVD, cancer, or everything else. So we split this up into these 3 subgroups, or we call cause-specific reasons for dying. And here we're looking at each of the omega-3 fatty acids individually in the blood. And again, the 10th percentile versus 90th percentile versus 10th percentile. The bottom one is EPA plus DHA, our favorite metric, because that's what we call the omega-3 index. And here is if we look here in all-cause mortality, 0.87 means same thing we saw in the figure below. That's a 13% reduction in risk for death, highest to the lowest. But if we look in cardiovascular disease, and just to back up, most people think about omega-3s and heart disease. But that's where their benefit is. And it's a little bit fuzzy outside of heart disease. Do they really have a role to play anywhere else? Well, this is an important finding here because our relative risk for death from heart disease was 0.85. That's a 15% lower risk of death, highest versus lowest for heart disease. But if you look at cancer mortality, here we have a statistically significant 11% reduction in risk for death from cancer with people who had the high omega-3. And then you go over to other mortality, which is everything, the entire kitchen sink of everything else people die from. And we have a significant 12% reduction. So it's about the same risk reduction regardless of cause of death. It kind of crosses the entire spectrum of what you might call non-health. Being dead is not being healthy. So this is, I think, an important finding that the omega-3s predict risk for death regardless of the outcome, of the cause of death. So I'll shut up and let you.
Well, I guess back to kind of comparing to other meta-analyses, sometimes on omega-3s, there seems like there's tons of them. And sometimes they find no effect, and sometimes they find an effect, and sometimes they're talking about omega-3s from a dietary intake study. Sometimes they're talking about, they're pretty rarely talking about blood levels. Is that right? Is this one of the biggest or one of the few
That's
that
true.
Blood levels
Right.
to meta-analysis? And how is that better or worse than the dietary intake meta-analyses?
Yeah, there's many more dietary intake based. And of course, dietary intake is based on somebody writing down or reporting a guess as to how much of what kind of food they ate over the last week, month, year. And then linking that guess with a approximate amount of omega-3 in a certain kind of food. I mean, it's a very rough way to actually get what we call the exposure. You know, what are you being exposed to? We're being exposed to omega-3. You can estimate it by these dietary questionnaires. They're cheap and easy to do relative to actually a laboratory test, but the information is much more sloppy and less necessarily trustworthy. What we did here is we certainly ranked it up to the next level, and we said we're going to look at blood levels, which is tissue levels essentially, and that's an objective marker of your intake, and that is a much more trustworthy way of deciding or of seeing the relationship between the omega-3 and the disease outcome than a diet questionnaire.
And sometimes people will take randomized controlled trials and put those together too. And these are all prospective cohort studies, large observational studies over time. So
Yeah. Nathan, you want to talk about the difference between those two study designs and what they tell us?
Yeah, sure. So in these prospective cohort studies, people aren't actively being intervened with. So they're not being told to change their behavior in some way. And so typically you try to get a large group of people, often representative of some population. And so, the cohorts here, as Dr. Harris said, representative of different countries or different parts of countries. And then you follow them forward for a long period of time, compared to a randomized controlled trial, which often takes place over a much shorter time interval. Not always, but often it'll be a much shorter time interval just because of logistics, because you're intervening with people and you have to make sure that they're compliant with whatever your intervention is. So in an RCT based on omega-3, often then people would be given a supplement for a shorter period of time and then followed. So I think one of the powerful aspects of this is, as Dr. Harris said, we can follow people for 16 years and use this independent measure of health, being the omega-3 levels in the blood. And so I think those add some additional benefits over the randomized controlled trials in this case.
yeah.
But to be clear, one of the weaknesses, the criticism of the observational study like we do is we measure their blood omega-3 levels when they're 60, and then we assume that it's going to be the same over the next 16 years, and we don't measure it. We can't measure it. So that's an assumption that underlies the observational stuff. And that's, it's fair. Nothing's perfect. There is no perfect study design. So you have to look at the strengths of both of these randomized trials and observational biomarker-based epidemiology.
Yeah. We have seen some interesting things with the omega-6s in some of these Force papers. Did you guys look at the main omega-6s, linoleic and arachidonic acid in this paper? Or is that something coming up?
We did not. We adjusted for them. Everybody, like Nathan said, everybody agreed ahead of time. What's the covariance? And the two covariates that relative to that are omega-6, linoleic acid and arachidonic acid in the blood. So these findings are the relationship between omega-3 and death outcomes independent of any effect of omega-6.
Okay.
I don't think we're even talking about, Nathan, doing an omega-6 focused trial.
Yeah, I don't think that's come up yet. I mean, it's true. You're right, Christina, that a lot of times Force has done both some omega-6 things and some omega-3 things. Just to follow up on your point about adjusting for omega-6. And back to our previous conversation just a few minutes ago about randomized controlled trials versus observational studies. So one of the ways that observational studies like this one try to get close to a randomized controlled trial is by statistically adjusting for these other factors. And so really the power of a randomized controlled trial is you say, okay, we're able to say this intervention causes or doesn't cause this change. We can get closer to that in an analysis like this by controlling for age and sex and BMI and part of the country and lipid compartment, and as we just talked about, omega-6s. But we can't rule out all of those other possible things. And so I think the power of Force is you get, 30, 40, 50 experts in the field from all these different cohorts getting their heads together to say what really might matter, what really might impact this, and let's account for that in our analysis. So when we're done, we feel really good about this finding, probably holding up against other people's potential. Well, what if it was X? We think we've accounted for a lot of those what if questions.
Can you quickly summarize some of the other things we accounted for in our analysis? I think we had having high cholesterol, having high blood pressure, having diabetes, smoking, right?
Yep. Alcohol consumption, a variety of demographics, including race and education, occupation, marital status, self-reported general health, which is kind of a catch-all that can actually capture a lot of other variation in people's health that wouldn't be better classified by things like diabetes status or alcohol status. I'm looking at the list. I think that covers most of them. Yeah.
It's a lot. I guess my last question is kind of focused on one of the compartments, the RBC omega-3, because that's the omega-3 index. What are the levels that the 10th and the 90th percentile represented for RBC phospholipids?
We calculated that and put it in the supplementary material here. But roughly, if you just look at the phospholipid category, the 10 overall average of the 10th percentile was about 3.4% EPA plus DHA, which fits conveniently with our original proposal 17 years ago that under 4% was high risk. And the upper end was like about 7.7% EPA DHA, which is pretty close to the 8% that we proposed again originally 17 years ago when we set up the omega-3. So this is pretty strong confirmation that those numbers are generally reliable, I think.
Yeah, I think that's really nice to be able to have some context. I think that's some of the good part about us being able to use omega-3 index and have that as something that you can have an idea of what high omega-3 levels mean, because there's so many different ways to measure it. It's not a standardized measure. So it's good to get a handle on. This isn't between people who are at 3% and 5%. This is about 4 and 8.
No, but recall, that's the 10th and 90th percentile. So that's
it's a big spread.
We're talking about only 10% of the people in this cohort had a level that's 7 or 8 or 9%. And if it was just the US, it would only be 2 or 3%, but this is worldwide. So we had some Japanese and some Icelandic people and
it looks like are you guys able or trying to recruit more types of cohorts that are from more like different parts of the world? Looks like Asia, North America, and Europe are pretty well, and Australia are pretty well represented. Are there other cohorts that you're trying to get after in other parts of the world?
Well, I don't think we've, Nathan, correct me if I'm wrong, but I don't think we've made any intentional effort to say, we haven't got anybody from Argentina here. We really need an Argentinian. And we go digging around the literature to see if anybody's done a cohort study and if they've measured fatty acids. This is a little bit more catch as catch can, and we run into cohorts occasionally, say, oh, we just added one in China that we didn't know about. And so
start the ability to start getting.
India would be a great one to add if there were something.
Yeah.
Almost the largest country in the world now, population, or just about.
Crazy. All right. Well, this is a really cool paper. I understand it took about 2 years to get it from conception
to birth.
Is
a long gestation.
long time, but not out of the question for paper, especially with that many authors and trying to get it done. So congratulations.
Thank you. Thank you.
List. And thanks for talking about it with us.
You bet. Good talking to you.
Thank
See you later.
Bye-bye.